All that, and they only managed to delay us by 6 minutes. So, how is everybody today? Good. I know that assignment 1 still needs to be released. I'm working on it. I had to make sure I had enough slides for today, so, you know, it is what it is. Yes?
You asked us how we were doing, but how are you doing, sir?
Thank you for asking. I'm feeling better, I guess. Yeah, I had a horrible Saturday. It was terrible. I won't regale you with the details, but oof. I don't want to talk about it. It was fine. I'm feeling better now. Thank you for asking. Everybody seems to have recovered. It's interesting. It's like I've had nearly continuous colds or flus in my household for the last month, and I don't think that's entirely attributable to the fact we've got a toddler in the house. You know, because honestly, I think we're now going to be paying the price for having 2 years of giving our immune system, all of our immune systems, the babiest of baby treatments that's possible, and now we're all going to pay for it. So, yay! Anyway, so, where were we? This is algorithms class. So, when last we were speaking, we were talking about big O notation. We developed the concept of big O mathematically as well as in intuitive terms. And now we just have a little bit to wrap up on the subject of big O notation before we jump into some other types that are related but not quite exactly the same. You guys can hear me at the back at this volume level? Wonderful. I love these swoopy lecture theaters. You can really just, you don't need the mic, But anyway. So, quickly recapping. Big O notation forms an upper bound for the time function that you intend to derive from the algorithm. In most cases, the actual going through the process of deriving the time function is long and tedious and probably unnecessary. You can make the leap immediately from degree of nestedness to loops to number of polynomials or the power of the highest polynomial term reasonably easily if you become familiar with the notation. But it is important to see it work through at least once in your careers, so we have done so. Of course, there are a couple of mathematical caveats to the big O notation. The first being that we are only concerned with the function inside the O being an upper bound for the timing function past some chosen point and not. You can select an arbitrary and not, so long as it's not infinity. In similar manner, the bounding function must bound the timing function, but only as it's multiplied against another arbitrary constant c. And that arbitrary constant is also allowed to be anything you like, so long as that's not infinity, right? So the mathematical, the intuitive mathematical principle behind all of this is if you have a function, right? If you have a function, let's simplify it. Let's imagine a linear function, right? No matter, if you select a constant function, right? Some value that's constant, never changing. That linear function is always going to cross it eventually, right? No matter how high you make the constant and no matter how low the slope of the linear function is, infinity happens to be a very long time. Those lines will eventually cross, right? So a constant is never a bound for a linear function, no matter how large the constant is or how small the linear growth is, right? Because you have literally infinity amount of time to wait for that crossing to occur. So the same principle is at play here. Does that all make sense? Good. So, that. So, it should be reasonably easy to demonstrate that the timing function is included in, if it's cubic polynomial, for example, it should be reasonably easy to select, prove that the bounding function applies for all functions which have a higher order of growth than that, right? All you need to do is select some particular n naught and c for which that is true, and that demonstrates the inclusion, right? If you want to demonstrate that t is not a member of some set of big O functions, how might you go about demonstrating this? Well, to say that some polynomial, such as 32n squared plus 17n plus 1, is not in something like, for example, big O n, which it is not, this is the same as saying that 32n squared plus 17n plus 1 is less than or equal to some c times n. We're sort of ignoring the n naught problem at the moment, but you can select some n here. Eventually we'll select some n. This is in turn the same as saying that 32n plus 7 plus 1 over n is less than or equal to some arbitrarily selected constant, which of course I just said is, not going to be the case eventually, right? So, no matter how large the c is that we select, 32n will always be larger for large n. Therefore, the inequality does not hold, and t at n, the timing function, is not an element of big O of n. Good. Another way of thinking of this is to use your idea of limits from calculus. All you did calculus in high school? A little bit? Did you cover limits at all? Have you guys? Everybody who has not covered limits, raise your hand. I can go through them briefly. Okay, everybody's on the same page then. Good. Good. So, all right, so that's big O. Big O forms the upper bound of a function. Fine, it's good to know an upper bound of a function. The upper bound, roughly speaking, corresponds to the worst case scenario runtime that you will ever experience with that function, which is useful to know because, it's kind of just like the law of universal pessimism, that you'll more often run into the worst case scenario or something close to it than the best case scenario or something close to it. So it's a good thing to know. However, we have two additional notations, big omega and big theta, which are also useful things to know and sort of derived in a very highly similar manner. So, big omega forms the lower bound of a function. Big theta is any function which is simultaneously the upper and lower bound, which is kind of interesting. It's like if you're in big O and in big omega, then you are in big theta. You have a question? Did I make a mistake on the slide?
No, I'm pretty sure in Greek, omega actually means like big O or long O. So it's
what? Are you serious?
yeah. So it's kind of funny. Like it's like it would also be kind of funny if it said big omicron, because omicron is little o.
So apparently in Greek, omega is like in Greek big or long O. So I had like a very nice mnemonic device to remember which one of these is which. So big O, you just have to remember that that's the upper bound, right? Then you've got big omega, and then you've got big theta. Lower bound, middle bound, upper bound. All right? So, and I'm not sure, but I wouldn't be surprised if that's the reason those letters were selected. So, anyway. So, basically, big omega is the same thing as big theta, but in reverse. Rather than requiring the timing function to be less than or equal to the function indicated multiplied by some constant past some n naught and then for all eternity, you are requiring it to be lower than that same value. So literally all we're doing is inverting the inequality, calling it a day. That's big omega. Make sense? So, considering the same function, which of these functions forms a lower bound for the given second order polynomial? Anybody want to shout it out? Yes?
The first three,
The first three.
they form the lower bound.
That is a correct but incomplete set of correct answers.
Oh,
Yes?
It's the first four.
It's the first four, yes. So here's the thing, right? Because the bound is arbitrarily selected. This is a very tiny piece of chalk. Oh my god, I need to replace the chalk. I need to get that guy back and replace the chalk in here. So let's imagine, let's make it simple, right? Let's just consider a linear function, right? Linear function. If we have big O of n, it's multiplied by some constant, right? So, what that actually means is that you have some, like, greater or lesser slope, right? So, this might be f of n times this constant, right? But the thing is, this might also be f of n times a different constant. Let's say constant big O, constant omega, right? So, in effect, one function can form both an upper and a lower bound because the constant itself might pop you above or below the function that you're trying to bound, right? Make sense? So in this case, the first four of these are lower bounds for that polynomial. As so. Once again, as with the case of big O notation, it's not especially useful to say that a constant function is the lower bound of anything, because that is literally the lower bound of literally anything. You can select C as being 0, I believe, or maybe 0.0001 or something like that, which is literally a lower bound to anything that doesn't asymptotically approach 0, which, if you do manage to invent a algorithm whose runtime asymptotically approaches 0 as the number of things you're trying to process increases, you should probably write a paper on it. Just saying. Probably the scientific community would want to know about that because you have managed to break the laws of causality. But anyway, so again, you want to try to pick a function which is maximally useful for describing the function that you're trying to describe. This means choosing a bound that's as close to it as is humanly possible. Right? Make sense? Any questions so far? Okay. So, yeah, we're kind of behind, so I'm going to skip this slide. So, this sort of leads us inevitably and inexorably to the third and final style of notation, big theta. So, in additional to best and worst cases, it's sometimes useful to consider the average running case. So, the manner in which you get average running time is generally something like you can perform what's called an amortized analysis, where you take, basically it's impossible to run the algorithm for all possible inputs because, of course, the state explosion problem, right? But you can, get a rough idea of how probable each thing is. Like, consider linear search, for instance, right? You have to start with the assumption that the thing you're looking for is uniformly distributed inside of the data structure, right? Which may or may not be a good assumption. But given that assumption, it is possible to calculate, how probable the worst and the best case scenarios are, right? And you can math it out, and you can do, a probability function for, on the number of, you can do all the math if you want. And as a result of that, you can derive a timing function for the average case, right? The average case is obviously a good measure to have if you can obtain it. However, again, you're usually going to have to make some assumptions about the data that's in the structure in order to be able to get there. And often your assumptions are fallacious, just because you're a human being. In practice, the average running time is often much harder to determine than the worst case running time. Analysis tends to become mathematically intractable. I just described how one might go about it for linear search, something very, very simple. And basically, rather than actually do it on the board, I was like, and you can imagine how it goes, Imagine how much less, how much less, desire I would have to get into it, and how much more hand-waving you would have seen if we'd have been talking about something complex like quicksort, But anyway. Also, the notion of average input frequently has no obvious meaning. It's reasonably obvious if you're doing a search function, because it's like, well, the item you're looking for can only be in so many different positions, right? But, how would one go about conceptualizing the average graph for the traveling salesman problem, for example? Oh, have you guys heard? Yeah, I had a comic about the traveling salesman problem, so anybody not remember what the comic was, or me talking about the traveling salesman problem? You guys all remember that? I'm getting very little audience interaction today. Awesome. When I ask you something like that, I need something from you guys. Okay. I know it's early in the morning, and I know that we didn't get started on time, so everybody kind of had those extra few minutes of sitting down to become sleepy. But, you do need to plow through this material. So in general, partially through, partially because of its ease of measurement, and partially because, it's useful to know what the upper bound is going to be on the execution of something. Plan for the worst, expect the best type of mentality, I suppose. We're still going to be worrying primarily about worst case runtime. Right? So, anyway. So, big theta is still a set of functions. The math has changed slightly. We now have two constants, C1 and C2. We still have this n naught concept. If t is between C1 f of n and C2 f of n, then t of n is in big theta. I hate this diagram. I didn't have time to redo it. The reason that I hate this diagram is because that is not an accurate representation of f at n times two constants. The functions are different functions. It annoys me. It shouldn't be in this. Okay, if I have time this week, I'll go back and redo it, and then I'll post an announcement saying, hey, I got rid of that graph I hated. But you guys see what I mean, right? Like, those are two different functions, which, like, it should be the same function scaled by different factors, but it's not, because of lack of attention to detail. Anyway, so, returning to our familiar polynomial function. How many of these statements are true? And which one particularly, if it is only one? Let me see if there's anybody else first. Yes, sir.
N squared?
Just n squared?
Yeah.
Let's see if you're right. You're right. Only n squared serves as the upper and lower bound for t. To find big theta, you must identify the best case scenario and the worst case scenario and see that those are, the best worst case and the worst best case are the same function, and then you have a big theta. Make sense? Any questions about any of that? Cool. All right. That's good. I like that one. No questions. Yeah. So, we just have a slight appendix to this material, and then we'll be jumping into studying an actual algorithm again. So, here are some notational abuses that are frequent with respect to big O and related notations. Number one, it is frequently the case that even trained computer scientists will say that the timing function is equal to big O of f of n. This is not correct. You should use the set inclusion symbol, the little backwards E thing, right? In fact, one may have noticed that certain tutorial documents for certain courses you might be taking at this very moment may have made similar errors in the past, which hopefully, I believe, have since been corrected. So, remember that these guys are sets, right? So you have to use set notation if you want to be technically correct. So, the domain of f of n is typically the natural numbers, right? It doesn't really make any sense to think of an array with 3.5 elements in it, right? Insofar as inputs are discrete, because, things in computers generally are discrete, that means that the domain of that function is the natural numbers. That's kind of funny because, when the stuff is graphed, it will typically be graphed as if it were a continuous function, right? But it's not, right? The mere fact of drawing a continuous line would imply that you could get to, you know, like, you could get to like 4.75 if you really wanted to, right? Not the case. Now, of course, if you have a sufficiently large domain of natural numbers over which you're graphing, it will certainly give the appearance of being a continuous function in the same way that if you run multiple frames of animation together quickly enough, it gives the illusion of movement, but it is only the illusion of movement. Non-negative functions. When big O and big theta and big omega, when we use these, we assume that the functions involved are asymptotically non-negative. So, given that this is number of inputs, and this is either time or memory, but normally time, we've been talking about time so far, does it make sense for this function not only to not like be like monotonically increasing, but like to dip below the x-axis, right? That would be to say that past a certain number of inputs, it takes negative time to process these pieces of information. Again, if you ever happen to develop something like that, please let the scientific community know, and tell us how building your tachyon particle generator went. For those of you who aren't into your like advanced science fiction physics, tachyons are particles that arrive before they're fired. Another way that you can find, in a sort of more numerically precise manner of finding big O, big omega, and big theta is to use limits. So, if you have two functions, f and g, if the limit as n approaches infinity of f over g is not equal to 0, or sorry, is not equal to infinity, then that's an upper limit. If it's not equal to 0, then it's a lower limit. And if it's not an element of either of those, then it's, wait, that doesn't make sense. I think those shouldn't be not equals. I think those should be equals. Uh-oh. I'll take this back and look at it. Yes.
On the practice of midterm exams out, you said like a lot of the functions were like you cannot use limits for calculating big N. Little big O, is that the same for this for these ones or?
To be honest, I haven't looked at the practice tests and I didn't write them. So
okay. Would you personally allow us to use limits or no?
I personally don't see the problem with it.
Oh.
So, yeah. If you want to use calculus, I don't see any reason not to use calculus. Yeah. Yeah, those should be equals. Jeez, I apologize for that. So, it's also possible to use big O notation with multiple variables. You just sort of expand your definitions appropriately along multiple dimensions and everything works out, right? So if we have some function t at m and n being an element of big O, f at m and n, this means that there exist constants c greater than 0, m naught greater than 0, and n naught greater than, there's another one, greater than or equal to 0, such that 0 is less than or equal to t, which is less than or equal to c times f at m, comma, n. So, for example, if we have t at t at m at n, yeah, oh my god. Should have bloody proofread these. I'm sorry. So if t at m comma n, that should be, is equal to 32mn squared plus 17mn plus 32n cubed, then t at m comma n is both in big O n cubed plus mn squared, and it's in big O m n cubed. So, it's not in mn squared, and it's also not in n cubed. You have to combine the approaches, right? You have to combine the polynomials. Any questions about that? So, here are some additional helpful results when reasoning about big O notation. If you are performing addition over two functions, big O f of n and big O g of n, that is equal to big O of f at n plus g at n. That, in turn, is equal to the maximum of those two functions. So, maximum with respect to orderedness, of course. So, if we have, n squared plus n, that in turn yields n squared, right? This one is considered the maximum in terms of the order of growth at any rate. Good. If you multiply two big O functions together, then the result is also multiplied. The big O can be collected out of it in the same way that you would collect a constant. So let's imagine that we have, with polynomials, right? Let's imagine that we have a t function which has some series of constants multiplied by increasing powers of n, with a at ad being greater than 0, so that being the final one. The limit as n approaches infinity of this guy is equal to ad, so the limit is neither 0 nor infinity. This, of course, means that it is which one? That guy on the bottom? That's theta. Thank you. So, also, for every r greater than 1 and every d greater than 0, n to the power of d is an element of r to the power of n. Because the limit as n approaches 0, nd over rn is equal to 0. Good. So, this is just one final slide to contextualize why all of this is important, or why runtime is important. Questions?
I did have one question about the multivariate and big O notation. If we have something like m over n, would that, like, do m and n increase at the same rate such that we would say that goes to 1, or can they increase at different rates such that it could go to infinity or 0?
I believe the proper way of conceptualizing, I believe the correct way of conceptualizing this is to, rather than thinking of it as, functions in 2 dimensions, think of it as planar geometry inside of a 3-dimensional space. Right? So, when you're describing the upper bound, you should be describing a plane rather than describing, a function of either of those 2 variables.
Okay, so basically either of them would be the increasing one.
Yeah, Now we're going to test the prof's drawing skills to the limit. Let's say you had, a volume, and let's say you had, something that was a plane that was going up like that, so that it was like that, right? So that's a plane. A rather uninteresting one. And then you had, an upper bound like that, upper bound like that, right? That's kind of the idea that we're going for in three-dimensional space, right? The equation that is determining the shape of this particular surface, I guess is the correct term for it. That's not going to be like directly decomposable in terms of the linear functions as presented over there, because although in this case I've basically just extrapolated from two two-dimensional functions and just sort of bridged across them. You can have surfaces that have like spikes in them and holes in them and all of that kind of interesting stuff, right? So all that complex geometry means that you have to have equally complex big O functions. Does that make sense?
Yeah.
I'm not going to put it on the test. Any other questions? Okay. So I won't dwell on this too long, but notice if we have so this chart assumes that we can process 1 million inputs per second, right? Or we can, you can see n at 1 million takes 1 second. That's sort of the baseline of this chart. For n log n, the same 1 million amount takes 20 seconds. For n squared, that takes 12 days, right? So to get it to a reasonable runtime, you have to reduce yourself to 10,000 inputs. By n squared, the only reasonable thing on there is 100. Sorry, that's for n cubed. For 1.5 to the power of n, even processing 50 will take 11 minutes. You can see that the next, to process 50 more points gets you to 13,000 years, which is, probably longer than human civilization, period. I think we're, as a species, 40, 50,000 years old or something like that? 150,000?
The civilization has been around for 12, 13,000.
12, 13,000, there we go. So that's as long as human civilization. So the fact that this thing lists 10 to the 17 years, and then after that says very long, should give you some impression of how long is. These are the types of numbers where if you took the universe and imagined inside of each atom of the universe there was another universe, and you kept doing that process 100,000 times, and on the final, all of the atoms of that final universe, you put one test case or put one thing to process. That's the orders of magnitude that we're talking about. Yes.
So when it says very long, is there actually a feasible number, or is this wait, it's a lot larger than 10 to the 25?
10 to the 25. Is 10 to the 25 years a feasible number?
Somewhat. Oh no.
Okay, good. Glad we came to that conclusion. Because I believe the universe itself is only 10 to the,
No, I mean, can you write it? No, is there wow. Is there like, did someone calculate those numbers or no?
Well, yeah, so they're easy to calculate. Yeah. Yeah, it's just,
A lot.
what do you get when you take 2 to the power of, 1 million? Something very, very, very large. Yeah, let's see, the Earth is something like 10 billion, 4 billion? 4.5 billion, yeah.
The universe is the 13.8 billion.
13.8 billion is the age of the universe. And a billion is 10 to the 9, so that's 10 to the 10. So 10 to the 10 is the age of the universe itself. So to run 30 elements through a factorial function takes you twice, it's not twice as long as the universe is old. It's twice the order of magnitude that the universe is old. So if the universe were a simulation, just say for argument's sake, and you decided to stop that simulation at this point, right, and rerun that simulation once for every year that's occurred in that simulation, that's like the order of magnitude amount of time we're talking about to process 30 bloody inputs. So, is factorial good? No. To process 10 takes 4 seconds, but basically 11 is impossible. And if 11 isn't impossible, 12 is surely impossible. So yeah, I'll put it to you this way, right? We don't even know if the universal constants will still be constant that amount of time in the future. We only really know that the universal constants have been constant over the period we've been measuring them, which is maybe a couple hundred years. So if there is very, very slight, imperceivable, undetectable variation in the universal constants that we haven't been able to pick up yet because our measuring equipment isn't sensitive enough and we haven't been measuring it long enough, we don't even know if computers work that far in the future, is what I'm trying to say, because we're not even sure that electrons will still exist. They'll probably exist, we hope. But, at a certain point, the big crunch comes along, So anyway, so that's why runtime matters. So here's just I see I've managed to talk about this long enough to avoid the next one. So we'll talk about union find next time. This is also a joke about time and infinity. I don't think it's technically true that if you had an infinite amount of time, that all algorithms would be constant time. They would still take the infinite amount of time, right? They would just effectively be constant because you could hop around in the timeline or something. But anyway, this is computer science, not exotic physics.